Hello everyone, we're gonna go over 5, 6, and 5, 6A and B today in this video. I'm gonna go pretty fast because there's a lot to cover, but feel free, please play it multiple times if you need to, slow it down, or just pause if you need to. I would suggest that you try to do some of these steps before I show you, but if you do get stuck, feel free to just watch through the whole video. If you just want the filled out completed notes, you can find it on Canvas. Just it's probably a PDF that's attached to the same modules as where this video is going to be. Okay, so we're going to talk about exponential functions, word problems mainly, about exponential growth and decay. Now there's a formula that's already in your packet that we're going to be using multiple times, and that's the APERT formula. So here they introduce this Q of t equals Q0 EKT. That's just different variables they're using, but it's pretty much exactly the same as APERT. So if you're more comfortable with using APERT, I would just use that because I will probably be referencing that throughout the video. Okay, so we're going to have our value. If your R value is positive, it's going to be a growth. If your R value is negative, it's going to be a decay. We have a rate of change of the this APERT function, and it's a little shortcut here that we're going to use in these notes. It's going to be A prime equals R times A. So the rate of change of APERT is equal to the rate times the A function. So you'll see me be referencing that when we talk about rate of change. All right, so the first problem here, example is talking about bacteria being grown, and they're giving us some reference points to find out some key information that we're going to need in order to help us with future steps. So it's saying that suppose that 10,000 bacteria are present initially in the culture and 60,000 bacteria are present 6 hours later. So what they're giving you is they're giving you a lot of key information, which we're going to talk about, but let's see what part A actually wants us to do. So part A says find the number of bacteria present at any time t. So what they're asking you really is to develop a function to determine the bacteria at any time. So you're not going to be finding an exact number for your answer. You're going to be creating a function, the APERT function, with a specific R value that will let you plug in any t value to get any number of bacteria at any given moment in time. So the first thing, we know we're going to use APERT, and this is all the information that they're giving us from the problem. So A, the accumulated value, if you want to reference our notes before, but the accumulated value is 60,000. The present value is 10,000. It takes 6 years to get that accumulated value, but we don't know the R value. So the first thing we need to do is we actually need to find the R value by plugging everything that we know into my APERT function, and we're going to solve for R for that. So when we get to that, you'll see that we have 6 equals e to the power of r times 6. And we learned about solving for e. We're going to ln both sides to get rid of the e. And then we divide by 6 to get our final r value. So the r is ln 6 divided by 6. We're going to keep it as that. If you put it in the calculator, you can try to do that, but you're going to get a really, really small number, and that's going to be really hard to work with. So we're going to keep r as ln 6 over 6, and we're going to find our final function by plugging our r value into the APERT function, so that I have a equals 10,000 equals 10,000 e to the power of ln 6 over 6 times t. So that is the final function. With this function, if I plug in any t value, I can get whatever number of bacteria is at that specific time. So we're going to use that function in part B and C to find out what we need. So in part B, it's asking us how many bacteria will there be in the culture at the end of 4 hours. So we're going to take our function that we got from part A, and we're going to plug in a new t value. We're going to plug in t equals 4. And at this point, you can put it into the calculator if you're comfortable enough. I would try now to see if you can plug this into the calculator and then check your work afterwards. So pause if you need to. And here is the answer. So if you calculated that, you should get 33,019.272 bacteria at hour 4. Okay. Now for part C, what is the growth rate of the population after 4 hours? So here we are finding the rate of change of our 8-part function. So as I referenced before, we're going to use that formula a prime equals r times the a function. And we want to find it after 4 hours, so that's why I'm plugging in 4. I know what a of 4 is. I just solved for that in part B, and I have the r function, or the r value. So I'm plugging in ln 6 of 6, which is the r value, and I'm multiplying it by the answer that I just got in the previous question, previous part. You're going to put that in the calculator. Again, see if you can get that before I show it. And that is what you should get. A prime of 4 is approximately 9,860.432 bacteria per hour. So I should be adding that, actually, bacteria per hour. Okay. So again, everything here is based off of APERT. You're going to plug in things into APERT. You're going to find the rate that it's changing at, and you're going to basically use that function for the rest of the problems. Okay, let's look at one more example using this APERT function. So we're looking at half-life. So half-life is a very common application of this decay, exponential decay. If you've taken science, you've probably worked with half-life at some point. But if you haven't, or you need a refresher, half-life is pretty much the time that is required for a given amount to be reduced to half of its original amount. Okay. For radium, in our example, the half-life is approximately 1,600 years. That means it takes 1,600 years for radium to get reduced to half its original amount. So we are starting with an initial amount of 200 milligrams. And again, first we want to find or develop a function to determine the amount left over after t amount of years. From looking at the problem that we have, we can see that t is 1,600, p is 200, a is 100, and again, r is missing. So the first thing that we're going to do is we're going to find r by plugging everything into the APERT function. Again, you're going to see that we're going to ln both sides after we isolate the e, and then we get an r value. Again, I'm keeping that in a non-decimal format because it is a really, really tiny number, and it's going to be a little harder to use in a problem. So I would just probably use ln of 0.5 over 1,600. We're going to plug in our r value into our final APERT to find that final function. Okay, a equals 200 e to the power of ln 0.5 divided by 1,600 times t. Part B asks us to find an amount left over after 800 years. So I'm going to plug in t equals 800 into the a function. I put that into the calculator with the t being 800, and that will be approximately 141.421 milligrams. Again, we're looking at now fast, so rate of change of the amount of radium present at 800 years. So we're looking for the rate of change at 800 years. We're again using that special rate of change formula. Okay, a prime equals r times a. So we're going to plug in 800 into a prime. So we'll put in the R value that we had in part A. We'll plug in the value that we got in part B, so that we get R times A of 800, which gives us a small rate, very, very low rate, but it's a decay, so it's negative 0.06127 milligrams per year. It's diminishing or decaying at a very slow rate, but it is decaying because the value is negative. Okay. D asks us for just a formula. Okay, how fast is the amount of radiant present changing after t years? So they don't know what they don't have an actual t value for us to plug in, but we know that we're going to set it up as a prime of t equals r times a of t. Okay, r again, we know r. We know what the a function is. That was all actually from part A. So we plug all that in. Okay, that was the r value here. This is our a value over here. And when we plug it in, we actually have things to simplify. So we're going to reduce the 200 over the 1,600 to give me a reduced value of 8. So that's why I end up with ln of 0.5 over 8. And that is my answer. That's my function of the rate of change at any given year of radium given my APERT function. Carbon dating. So carbon dating, they use that to the fact that they know that carbon-14 has a half-life of 4,730 to date fossils, date bones that have been decaying probably for a long period of time, and it is a very commonly used one, specifically in biology. Okay. So first thing, what is the decay constant? Well, pretty much that's just finding the rate at which it's decaying. So we are finding that R value. Okay. Okay. It's half the amount is left after 5,730 years. So the one thing is they don't give us a starting amount or an ending amount, but what we can do is we can assume that if P is 100, the starting amount is 100, then the accumulated amount, the final amount should be half of that. It should be 50 after 5,730 years, since that is the half-life. So it really doesn't matter what your starting value is, as long as your starting value is going to end up being half after the full half-life has happened. Okay, so you can do P equals 1,000, but A would have to equal 500. I just use 100 since it's easier. It's like 100%, and after a full half-life, then 50% would be left. That's why A is 50. So we want to find R. That's the decay constant. So what we're going to do is we're going to plug in all of our values to find R, and again, I'm going to leave R as a whole function or whole expression instead of a decimal, since it is going to be a very, very small number. So R equals ln of 0.5 over 5,730. And that's again using ln's. We're going to ln both sides of the equation to help us get rid of the e and solve for R. So we're using that same formula. We're going to use R. In this scenario here, it says that a skull from the archaeological site has 1/10 of the amount of C14 that it originally contains. Determine the approximate age of the skull. So what we know is that the final amount is 1/10 of the original amount. So what we can assume is that the p-value, if the p-value is 100, then the final amount has to be 1/10 of that, which is 10. Okay, so we're going to use p equals 100, a equals 10. I know my R value from my previous problem, and they want us to find the time, the age of the skull after only 1/10 of the carbon-14 is left over. Okay. So again, we're going to use APERT. We're going to plug in all our values that we know, and we try to solve for t. A lot of this should be very repetitive now. We have a lot of ln's that are happening, so I'm going to ln both sides, and I try to solve for t. So here there's something that's attached to t, and I want to get rid of this ln 0.5 over 5,730. So what I can do is I can multiply by the reciprocal, which is what I do in this last step. And that's why that fraction is flipped, because I'm multiplying by the reciprocal in order to move it to the other side of the equation. And that is what t equals, but I'm going to calculate it so I know like what that time is. So I'm going to put that on the calculator, see if you can get that. Pause if you need to. But t, when you put in the calculator properly, it should be an approximate age of 19,034.648 years. So the skull was approximately 19,000 years old. Okay, so that's using APERT. Finding, a lot of these problems was finding r first, putting r back into the function, and then now you have a function that allows you to find any time or any amount at any given time. Okay, we're going to move on to learning curves and logistics growth. So learning curves is just another application of exponential functions. Learning curve essentially is, when you're starting something new, you learn a lot and you have a lot of progress, but at some point, when you're getting more and more experience, when you have less and less to learn, it starts to plateau. You start to grow less as time goes on, because it's just diminishing returns on the amount of time you put in and how much improvement that you get. This, again, happens a lot in school, happens a lot in athletics. What else? Music. Anything that you're learning, you're probably going to start plateauing at some point, and that can be modeled by exponential functions. Okay, so we're just going to go into the first example. I will most likely be giving you a function to work with when we are working with learning curves and at the end of the notes here, logistic growth, but we'll just need to know how to work with it and what that question is asking us for. So in our first example, a camera division of Eastman Optical produces a 35 millimeter single lens reflex camera. Easton's training department determines that after completing the basic training program, a new, previously inexperienced employee will be able to assemble model F cameras of this function per day. So that is their learning curve. Okay, so depending on how much time that they have been working at the assembly line, we're hoping that they can improve their skills and work at a better pace. Okay, so for A, it says how many Model F cameras can a new employee assemble per day after basic training. So after basic training, that means they're fresh. They haven't had any work experience yet. So we can say that would be t equals 0 because we're just starting. So all we're going to try to do is we're going to plug in 0 into our function. And we can use a calculator. You can actually do this by hand. We can simplify that power to get 0. E of 0 or anything to the power of 0 is 1. So we're really just doing 50 minus 30, which means when you're fresh into the job, new employees are probably going to be making 20 cameras per day. So we're hoping to see growth as time goes on. We're hoping to see that they are increasing their daily output of cameras. So hopefully we'll see like more than 20 in part B. In part B, they're asking us what about when an employee has 1 month of experience or 6 months of experience. So just like in part 1, but we're going to plug in different t values. We're going to plug in t equals 1 and t equals 6 into the original Q function. And using our calculators, you should get 31.8 when t equals 1 and 48.5 when t equals 6. And since we can't have partial cameras, we're just going to round up to 32 cameras per day and 49 cameras per day. Part C, how many Model F cameras can the average experienced employee ultimately expect to assemble per day? So this is saying, like, as time goes on, if you're getting really, really, really good, what's that cap? Like, when you're working as efficiently as you can, there has to be a cap. You can't make infinite amount of cameras per day. It's not a constant rate. And this is why we talk about learning curves. There has to be a peak, a plateau. So what we're really doing is we're saying, if, let's say, hypothetically, this employee has been working there for 30 years, okay, that's a lot of months. So you can plug in a really, really massive number, or you can plug in infinity. So we're finding limit as t approaches infinity into our Q function. So we just want to think about plugging a really, really big number. You can do this in two ways. You can use your calculator to just plug in, a million or a really, really big number, and you'll see that it starts plateauing. Or you can do it by hand here, which is actually quite straightforward. When we were learning about limits, we do direct substitution first. So when we direct substitute infinity into our function, you can see that I'm going to have 30 over e to the power of 0.5 times infinity. Okay, I brought the e down because it's a negative power, so I can drop it down to the denominator to get rid of the negative power. And e to the power of 0.5 times infinity, that's going to be a massive number. Okay, it's going to be huge. So 30 over infinity is essentially 0. Okay, think about that. A tiny number over a really big number, that's going to be a really, 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 really small number, or we can say it's 0. So we're really doing 50 minus 0. So at most, an experienced employee can make an average of 50 cameras per day. That is that upper threshold, upper limit. Right. So let's look at another example of this this plateau effect with logistic growth. So this is another function. We're not going to be memorizing this function, but you'll need to be able to recognize that this is a logistic growth problem, and just make sure your answers align to this plateau effect. Okay, so starting with this example, the number of soldiers at Fort MacArthur who contracted influenza after T days during a flu epidemic is approximated by the exponential model. So I am providing this function for you. This is what a logistics growth function looks like. Part A, if 40 soldiers contracted the flu by day 7, find how many soldiers contracted the flu by day 15. So this is a logistics growth function, because during a surge of an epidemic, there's going to be a lot of people getting sick. But as time goes on, we're hoping that that slows down, because there's less and less people that are going to be able to be infected, and hopefully there is some prevention program to prevent people from getting sicker. So hopefully that it's not exponential, that they're going to start plateauing at some point. Okay? So what they gave us is, at day 7, there were 40 soldiers that had contracted the flu. So that is our reference point. So 7, I'm going to plug into, actually I'm not going to plug anything because they actually gave that to us. So we know we have a reference point of 7, 40. So 7 is the t value, and 40 is the output, Q of 7. So just like the other problems, I want to find the rate. This time K is our rate, and I'm going to plug in that reference point 7, 40 into my logistics growth function, so that K is the only remaining variable. Again, E is not a variable. E is like pi, so it's just referring to a really, really long decimal. So K is the only variable that we have. I'm going to now attempt to try to solve for K. So if we look back in some exponential function notes from 5.1, this should look really familiar. We're going to try to solve for K, but K is in the denominator, So we're going to multiply that entire denominator over to the left side. So we're going to move it over to the left, and that will bring the k value out of the denominator. Okay. So when that happens, I have 40 times that entire denominator equals 5,000, and I'm going to slowly chip away at the left side, and I'm going to break down that left side so that I can get k by itself. And again, you're going to see that I'm going to ln both sides in order to get rid of the e value. And I get another really kind of, it looks really complicated for a k value, right? We can leave it like that. For our purposes here, I think it is a value that is more manageable than the other ones that we've done. So when I put this in the calculator, I get k is approximately 0.3299738, and it goes on for many more decimal places. So if we're using our calculators properly, hopefully we know how to copy and paste, because we're going to be referencing this k value a lot. We're not going to round. We're going to use our calculator functions to our advantage, and we're going to be able to copy and paste this entire decimal so we can try to keep our answer as accurate as possible. So I'm going to take that k value and I'm going to plug it into the function along with the day that I want to find. I want to find the amount of soldiers contracted the flu by day 15. So I'm going to plug in the t value of 15 and my new k value that I just found into my function. It's going to be 5,000 and over this entire expression on the bottom. Now, just to make sure when you're plugging into the calculator properly, you want to make sure you put parentheses around that entire denominator. Okay? So try to do this. Don't just copy down this decimal as a final answer, because if you're not going to be able to get this, you want to make sure you let me know so I can help you out the next time I see you. So when I plug it in, you should get 507.55, which we're going to round to 508 soldiers were contracted in total by day 15. For part B, at what rate is the number of soldiers contracting the flu changing at day 15? So it's a rate problem. We're not going to use that a prime equals r times a, because that's only for apert. This function is not written in an apert format. It's written in a fraction format. So therefore, if I want to find the derivative of q prime, I need to do quotient rule. I want us to take a moment, try to set the quotient rule. It's going to look a little bit lengthy, but it's going to simplify nicely so that it won't be as long. Okay, so try to do that. We're going to start with q with the k value plugged in that we found here. I'm rounding it to negative 0.33. You can choose to round it to negative 0.33 or take that entire decimal with your calculator function, and I'll take either one. I'll probably have a margin of error when you're taking the test, but essentially you're going to do quotient rule here, and when you perform quotient rule, that is what you should get. So take a moment. If you need to pause here, but make sure you can match up all these parts or see where each of these parts came from. Now, what's nice about this quotient rule is that first entire part turns to 0. It goes away because it's multiplying by 0 to the whole thing. Right here. The whole thing turns to 0. So that's going to go away. So you're left with just that second part of quotient rule. And I'm going to do my best to simplify that as much as I can by multiplying the coefficients together, the integers. And you're left with q prime equals this. That's 2,060,850 e to the power of negative 0.33t over 1 plus 1,249 e to the power of negative 0.33t squared. Okay. So I'm doing my best to simplify as much as I can, so when I plug into the calculator, it's not as cluttered and there's less room for mistakes. So what we're plugging into this q prime is we are plugging in day 15. So t equals 15 into my function. And I'm going to calculate that to get 150.14. So again, I do want you to try to plug this in. And if you need to, make sure you put parentheses around this entire bottom to get a correct answer. So 150.14 is your target calculation. And I'm going to approximate that and round that up to 151 soldiers per day. And that is logistics growth. So you've seen two applications of a plateau effect, a learning curve, and a logistics growth. Both requiring you to find a k value by plugging in a reference point and developing a function with that k value in order to find whatever t that they're going to ask for. So again, that is 5.6, A and B. Go back to any part that you need to fill out the notes. Hopefully the explanations were clear enough. Again, if you just want to look at the full filled out notes, you can find a PDF on Canvas.